Yesterday we saw that the derivative of sine was cosine and that the derivative of cosine was negative sine. So once again, these are all in the formula sheet for you. You don't have to memorize them, but we'll look at the derivatives of other trig functions today, starting with y equals tan x. So we can determine that by saying that tangent is sine x over cos x, and then use the quotient rule to differentiate. So dy by dx is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So when you multiply these out, you're going to get cos squared x plus sine squared x all over cos squared x. Cos squared x plus sine squared x is 1, and 1 over cos squared x is secant squared x. So the derivative of tan x is secant squared x. In the same way, we can get the derivative of cosecant x by saying it's 1 over sine x, and then again using the quotient rule to differentiate. In this case, the derivative of the top would be 0 because the numerator is a constant, times the bottom, minus the derivative of the bottom, which is cosine x, times the top, all over the bottom squared. So you're going to get negative cos x over sine squared x, which you can break up to negative cos over sine times 1 over sine, and negative cos over sine is negative cotan, and 1 over sine is cosecant. So there we go. The derivative of cosecant x is negative cotan x times cosecant x. And we have the other derivatives, which we could find in exactly the same way, but there's a list of the rest of them. We've done derivative of sine, we've done derivative of cosine, tangent, and cosecant. We'll just state the derivative of the last two. The derivative of secant is secant tan, and the derivative of cotan is negative cosec squared. So notice that the derivative of all the co-functions are negative. The derivative of cosine is negative, the derivative of cosecant is negative, and the derivative of cotan is also negative. So again, these are on the formula sheet. Don't have to have all these memorized, but you have to know how to use them, and in many cases it involves using the chain rule like we saw yesterday. So to differentiate number 1, there's a couple different ways you could do this one. One of them would be to write f at x as 1 plus tan x all to the negative 1. And then we can differentiate using the chain rule, which tells us that we're going to bring the exponent in front as a coefficient. The power decreases by 1. And then we find the derivative of what's inside the bracket, the derivative of 1 plus tan x. So that'll be negative 1 over 1 plus tan x all squared times the derivative of 1 plus tan x. The derivative of a constant 1 is 0, plus the derivative of tan x is sec squared x. And so now if we multiply the negative 1 times the secant squared x, it'll be negative sec squared x over 1 plus tan x all squared. So there's the value of that derivative. So again, in most cases, the chain rule is being used when you're differentiating these trig functions. Number 2, that would be the same as 2 times the cosecant of 3x squared all cubed. So to differentiate this, again, we have to use the chain rule. So dy by dx will equal. So the first step, the 3 comes in front, and it's multiplied by the 2. The power decreases by 1, and then we multiply by the derivative of what's inside the bracket. The derivative of the cosecant of 3x squared. So to differentiate that, again, we need to use the chain rule. So if we look back, the derivative of cosecant is negative cosecant x times cotan x. So when you differentiate that, it'll be negative cosecant of 3x squared times the cotan of 3x squared. But then you have to multiply once again by the derivative of what's inside the bracket. Let's give myself a bit more room here. So again, we need to multiply by the derivative of what's inside the bracket. So the derivative of 3x squared. And the derivative of 3x squared is 6x times the 6 in front here will give us 36x. Now the other thing we can do is we can combine these next two factors. You've got a cosec squared of 3x squared times a negative cosecant of 3x squared. A negative times a positive is a negative, so that negative will come in the very front. And when you multiply cosec squared 3x squared times cosec 3x squared, that'll give us cosec cubed 3x squared times the cotan of 3x squared. And so there's the derivative using the chain rule. Number 3, notice we have a variable of y there, which means we have to use implicit differentiation. So when you differentiate tan of y, the derivative of tan is sec squared y. And then remember, whenever you're using implicit differentiation, you also multiply by the derivative of what's inside the brackets. That would be the derivative of y with respect to x, which gives you dy by dx. And on the right side, when you differentiate that, you'll just get 2x. And then remember, we get dy by dx by itself. So it'll be 2x over sec squared y. And there's something else you could do here if you wanted, because this is the same as 2x over 1 times 1 over sec squared y. Basically, that is the reciprocal of secant squared, and the reciprocal of secant squared is cos squared. So we could say this is 2x cos squared y. So again, that's a step that they might do on the unit circle, or excuse me, in the answers in the book. If you're checking answers, they probably would do that step. So that is where it comes from. Next one says determine the slope of the tangent line to y equals the tangent of cosecant x when sine of x is 1 over pi and x is between 0 and pi on 2. So we are in the first quadrant. So to do this one, notice that it's the tangent of the cosecant of x. So we will use the chain rule when sine of x is 1 over pi in the first quadrant. So first step, the derivative. The derivative of tangent is sec squared. And remember, you're always keeping the same argument. So it'll be sec squared cosecant x times the derivative of what's inside the bracket. We always use the chain rule. And the derivative of cosecant x we saw is negative cosecant cotan. So that'll be the sec squared of cosecant x times negative cosec x cotan x. And so we can simplify that a little bit. That negative can come in the very front. But in this case, we cannot multiply the cosecant by the negative cosecant because this cosecant belongs to the sec squared. It's sec squared of cosecant x. So we actually can't multiply these two together and simplify it because the first cosecant x is the argument. It's part of the secant squared. Oh, great. Thank you. Okay, so there's an expression for the derivative, and we need to find out what its value is when sine x is 1 on pi and x is between 0 and pi on 2, which means that we are in the first quadrant with a terminal arm and a reference triangle. X, the reference angle, is always between the terminal arm and the x-axis, and the definition of sine is that it's opposite over hypotenuse. You can find the length of the missing side using Pythagorean theorem. So if we say that A is 1 and we want to find B, the other leg of the triangle, the hypotenuse pi then is squared, and so B squared will equal pi squared minus 1, and B will equal the root of pi squared minus 1. And that'll be a positive because you're going to the right from the origin. So now we can evaluate what the derivative is, which remember tells us the slope of the tangent, using that triangle. We're going to have sec squared of the cosecant of x. So cosecant is reciprocal of sine. If the sine is 1 over pi, then the cosecant will be pi. And that's multiplied by the cosecant of x, which again is pi, times the cotan of x. And cotan is, well, tangent is opposite over adjacent. So the cotan will be adjacent over opposite. Pi squared minus 1 over 1, or pi squared minus 1. And we can go further here because we can evaluate what the secant of pi is. If we look at pi radians, which is over here, did I forget the negative? I did, yeah. Pi radians is here, and the coordinates there are negative 1, 0. Secant is the reciprocal of cosine. The cosine is negative 1 over 1, and the reciprocal of that would be still negative 1 because it's 1 over negative 1. So now this is going to give us a negative 1, but that one's going to be squared, times pi squared minus 1. It is, yeah. I didn't write it on there. There we go. And so when you square the negative 1, obviously that's 1, but the negative sign in front of that will keep it negative. So it'll be negative pi times the root pi squared minus 1. So there's the value of the derivative at the point where the sine of x equals 1 over pi in the first quadrant. It is found by, it gives us the slope of the tangent. Okay. The last one, prove that y equals secant x plus tan x is concave up on that interval between negative pi on 2 and positive pi on 2. So we use the second derivative to determine concavity and any points of inflection. So that's what we need to do. So the first derivative, dy by dx. The derivative of secant x, if we go back, the derivative of secant x is sec x tan x. Plus the derivative of tan x is sec squared x. So there's our first derivative. And in this case, I mean, you could, if you wanted to, take out a common factor of secant x, which will give us tan x plus 1. You're going to have to use the product rule to differentiate this, but you would have had to use the product rule up top anyways, because the first term is a product. No, I took out a common. Yeah, it is, absolutely. Not on my game today. Thank you. Okay, so now we'll take the second derivative. D squared y over dx squared. So using the product rule, the derivative of the first, the derivative of secant x, if again we go back, the derivative of secant is sec x tan x. So this will be sec x tan x times the second factor plus the derivative of the second factor. The derivative of tan x is sec squared x plus the derivative of sec x is, again, tan x, or sec x tan x, times the first factor, which is secant x. So again, we differentiated using the product rule. The derivative of the first factor, the derivative of secant is sec x tan x, times the entire second factor, plus the derivative of the second factor. There are two terms there. Derivative of tan x is sec squared x, plus the derivative of sec x is sec x tan x, times the first factor of secant x. So we can definitely simplify this a little bit. I've got two terms here. Let me underline that. Two terms there. They're going to be multiplied by the factor in front. So when I first multiply by tan x, that'll give me sec x tan squared x. And then when I multiply by secant x, the second term inside the bracket, I'll get sec squared x tan x plus, same thing here, I've got two terms. I multiply them both by secant x. Sec squared x times secant is sec cubed x plus sec squared x tan x. And now I can see that I actually have two terms that involve, or two terms that have sec squared x tan x. So I can combine them. I write them in order of descending power. I've got sec cubed x. I've got 2 sec squared x's tan x's, and I've got 1 sec x tan squared x. And there's one more thing that we can do here. There is a common factor of secant x that we can take out, which will give me secant squared x plus 2 sec x tan x plus tan squared x. And when you do that, I think we can factor that trinomial. This will all make it easier to evaluate for our different values on our number line. It should be sec x plus tan x all squared. So that just makes it a whole lot simpler. Because remember, when we want to find out where our concavity changes, where our points of inflection are, we have to find the critical numbers of the second derivative, which are where that equals 0. So if you can factor it, that's what we've always done. So our solutions will occur where the secant of x equals 0 and where sec x plus tan x all squared equals 0. Now, we want to find out what's happening between negative pi on 2 and positive pi on 2. So, here's negative pi on 2 there. Positive pi on 2 is here. If we use the CAST rule, we're in the C quadrant and the A quadrant. So everything's positive in the A quadrant. In the C quadrant, cosine is positive, which means the secant is positive. So in this case here, we actually don't have to find our critical numbers because the first factor is always going to be positive. And so is the second factor, because no matter what you get inside the bracket, it's going to be squared anyways. So that we don't even have to find our critical numbers. We just have to look at the unit circle and use the CAST rule. So in the domain or interval negative pi on 2 to pi on 2, secant x is always going to be greater than or equal to 0. As well, it doesn't matter what quadrants we're in, the second factor is also going to be greater than or equal to 0. They will never be negative, so therefore the function is concave up. So again, by using the CAST rule, we didn't even have to find our critical numbers. We didn't even have to set up our number line and find the value of the second derivative in the intervals. Okay? So what you should work on, page 319 to 320, 1A through J, and then for questions 2, 3, and 9, for each of these questions, you do A and B only. A and B from number 2, A and B from number 3, A and B from number 9. We'll be having an exam.